liquids and solids. In order for us to talk about substances that are in the liquid and the solid state, we need to refer to the way that the particles are held together. So we're going to talk about the term intramolecular forces first, and it's actually something we've been dealing with all along, we just haven't called it that. In Chapter 8 and Chapter 9, we looked at how molecules are formed from their atoms. We said that the forces that hold atoms together in a molecule are ionic and covalent bonds. But now we want to look at the forces that hold particles together in a liquid or a solid state. And we refer to substances in the liquid and the solid state as condensed states. So these forces could be covalent or ionic, but they also could be much weaker interactions, which are called intermolecular forces. So we know prefixes. Let's think about this. Intra means within, and inter means between. So if we deal with intramolecular forces, we're looking at forces that hold atoms together within a molecule, like our ionic and covalent bonding from Chapter 8 and 9. If we talk about intermolecular forces, we're going to look at the forces that hold particles together in a solid or a liquid. So we want to deal with changing states to get a better way of understanding these intermolecular forces. So if we have a substance and we change it from a solid to a liquid, or a liquid to a gas, the molecules stay together. All we're doing is breaking the forces that are holding the molecules together in that condensed state. So when we deal with state changes, they're changes that are due to the forces among the molecules, which we refer to as intermolecular forces, and not for the forces that hold atoms together within the molecules, or intramolecular forces. So let's use water as an example. Let's say that we start out with water in the solid state, and we add energy in, and we turn it to the liquid state. It's a physical change. We're melting water. And when we melt water, we have to add in 6.02 kilojoules of energy for every mole of solid water that we convert to liquid water. And we're breaking intermolecular forces when we have that phase change. Well, now let's say that we're taking liquid water and we're adding energy in and converting it to gaseous water. Well, we're looking at a phase change again. Going from a liquid to a gas means that we are boiling the water. And we do have to add in more energy in order to break all those intermolecular forces that are holding the substance together as a liquid. So we would have to add in 40.7 kilojoules of energy for every mole of water that we want to change from the liquid to the gaseous state. But now let's say that we've got water in the gaseous state and we want to break the bonds within the water molecule, those oxygen-hydrogen covalent bonds. Now look at the number. We would have to add in 934 kilojoules of energy per mole of oxygen-hydrogen atoms we would want to break. So in other words, it takes a lot more energy to break up molecules or to break intramolecular forces than changing the states of matter and disrupting those intermolecular forces. So let's review polar bonds that we talked about in Chapter 8. We know that when we look at polar bonds, we're looking at an uneven distribution of electrons. One of the atoms in that bond has a greater electronegativity than the other, so we end up with a center of positive charge and a center of negative charge within the molecule, which gives us a dipole moment, a positive and negative end of the molecule. Well, what that leads us to is a type of intermolecular force called dipole-dipole intermolecular attractions. Molecules that have dipoles, or positive and negative ends to them, will be attracted to each other, and they'll line up to maximize the attractive forces and minimize the repulsive forces. Now, these intermolecular forces are much weaker than our intramolecular forces like ionic and covalent bonds. So dipole-dipole intermolecular attractions are about 1% the strength of a covalent or an ionic bond. And they become weaker as the atoms get farther and farther apart. So here's a model. Up at the top, we've got two molecules. The molecules are held together by polar covalent bonds, which gives us a dipole moment within each molecule, a center of positive charge and a center of negative charge. Now, because each of our molecules has a positive and a negative end, there's going to be an attraction between the molecules. That red dotted line represents the intermolecular force that's attracting those two molecules to each other. So down below we've got an aggregate of these molecules, and notice that the positive end of one molecule is attracted to the negative end of another molecule. Those pink dotted lines represent those intermolecular dipole-dipole attractions. And at the same time there'll be repulsive forces between the negative and positive ends of those molecules. Now let's look at a specific example. We can look at a water molecule, which we've seen before. We know that we've got a polar covalent bond holding each of the hydrogens to oxygen. Oxygen has a greater electronegativity than hydrogen does, so we end up with a polarity within our molecule. We've got a dipole set up where the negative end of our molecule is the oxygen end and the positive end is our hydrogen end. Well, now over on the right-hand side, we look at a model that shows us those intermolecular forces between water molecules. And those are represented by the blue dots between the water molecules. And notice that the oxygen end of one water molecule is going to be attracted to the hydrogen end of another water molecule. Positives attract negatives. Now, the intramolecular polar covalent bonds that hold the water molecule together is a much stronger force than the intermolecular dipole-dipole attractions that are holding each of the individual water molecules together in a liquid or a solid. That's why it takes less energy to break that intermolecular force than to break the intramolecular force within the water molecule. Now, there are varying strengths in dipole-dipole intermolecular forces. When we look at hydrogen bonded to another highly electronegative atom within a molecule, we're going to have a large dipole set up within that molecule. And specifically, we're looking at when hydrogen is bonded to nitrogen, oxygen, or fluorine within a molecule. Because the bonds are so polar, the dipole moment within that molecule is greater, so the intermolecular forces between molecules is going to be stronger. And we call these extra strong dipole-dipole intermolecular forces hydrogen bonding. And the hydrogen bonding, or that strong dipole-dipole intermolecular force that forms when hydrogen is bonded to nitrogen, oxygen, or fluorine within the molecule, is due to the great polarity within the molecule and the close approach of the dipoles because hydrogen is so small. So here's an example of the boiling point compared to the atoms within the molecule. And we should notice that the higher the boiling point, the stronger the intermolecular forces. In other words, it takes more energy to break stronger intermolecular forces than weaker intermolecular forces. And if we look at the beginning of each of these lines that are graphed, we see water, hydrogen fluoride, ammonia, and methane. And notice that water, hydrogen fluoride, and ammonia have much higher boiling points than the rest of the trend within their particular group. And the reason for that is because hydrogen is bonded to oxygen in water. It's got a stronger polarity, so it's got stronger intermolecular forces. so it requires more energy to break them or to boil water. And the same for hydrogen fluoride, and the same for ammonia. Once we get further down the group, we don't have as strong an intramolecular force within the molecule, so the intermolecular forces between the molecules is weaker, so the boiling point is weaker. Now what about molecules that don't have dipoles? Okay, even those can form solids and liquids. Okay, even they can exert forces on each other, but they are much weaker than our hydrogen bonding or our dipole-dipole bonding. And again, we know that we have these intermolecular forces between molecules that don't have dipoles because they do exist as liquids and solids. So we can assume that the electrons in atoms are uniformly distributed at every instant, but that's really not true. At any given instance in time, the electrons may be unevenly distributed within an atom. So atoms can develop a momentary non-symmetrical electron distribution, and what that would produce is a temporary polarity within that atom. Or if we're looking at a nonpolar molecule, we could at an instant in time have an uneven distribution of electrons and again form a temporary charge between or within that nonpolar molecule. And what will happen is this instant dipole in one atom or molecule will cause an instantaneous uneven distribution of electrons in another, and that will pass on from atom to atom or molecule to molecule. And what we're dealing with here are very weak intermolecular forces called London dispersion forces. Sometimes they're referred to as LDFs for short. And these forces have to be strong enough to produce solids even out of things like noble gases. And you may think, well, noble gases are gases. But we can change them into liquids and we can change them into solids if we cool them down and add enough pressure because of these London dispersion forces between these nonpolar atoms. So let's look at an example. Let's say that we have in the left-hand side here, we've got atom A and atom B. And the electrons are distributed pretty much evenly in both of those atoms, so there's no attractive force. But let's say as we move down on the left-hand side, that for an instant in time, the electrons are more collected on the left-hand side of the molecule than the right-hand side. It's just probability. That's going to give that atom an instantaneous dipole. It's going to have a partial negative and partial positive end. And what that will do is it will influence atom B. The partial positive end of A will attract electrons in B and set up another instantaneous dipole in B, and that will continue on down the line. If we look over on the right-hand side, we're looking at the same general idea, except this time we're looking at a molecule. We're looking at a diatomic molecule, hydrogen. And up along the top, molecule A and molecule B have an even distribution of electrons, and there's no attractive force between those two molecules. But again, let's say that for an instant in time, the electrons in hydrogen on the left-hand side are not distributed evenly. For an instant, the electrons are piled up more on the left-hand side than on the right-hand side. That will make that molecule have an instantaneous dipole. And that instantaneous dipole in molecule A will induce a dipole in molecule B, because the positive end of the left-hand hydrogen molecule will attract the electrons in molecule B. And that attraction between those instantaneous dipoles is what we refer to as London dispersion forces.